Jai Hind, my dear students. Today I am going to start a new topic, virtual memories and implementation. I am Akhil Sharma, Associate Professor in Department of Computer Science and Engineering. This course is under code BCS 302. Let's start the virtual memories. We know that there is an important challenge in the design of a computer system to provide a large and a fast memory, and we need to have an affordable cost. So architectural solution that increase effective speed and the size of the memory is a requirement for the system. So we understand and known earlier that the cache memory were developed to increase the effective speed. So what is the purpose of virtual memory? So virtual memory is an architectural solution to increase the effective size. So earlier the size was limited, now it will be more available for the operating system and the program to utilize. Now the addressable memory space depends upon the number of address bits available in the system, and usually it range from 8, 16 or 32. So for example, if 32-bit address is available in MAR, okay, so the MAR register is having a value 32-bit, okay, so the addressable memory is 4 gigabytes. That can be easily calculated. We very well know that 2 raised to power 30 is equals to 1 G, okay. So when we add additional 2 bits, so we get the space of 2 raised to power 2, that is 4. So that will come out to be 4 gigabytes space if one cell is having 8 bits. The physical memory in the computer is generally not large as the entire possible address space. So 4 GB address space is supported by MAR, but actually we are having a small memory size like 1 GB. Nowadays computer has advanced, so the number of address bits has increased from 32 to more, and the address can be more than 4 GB bytes like 8 GB, 16 GB and so on. Okay, so it should accommodate the lower space and the maximum addressable space. This is a available address space, and this is the limited by the availability of user, okay, 1 GB. So large program that cannot fit into completely into the main memory have their parts stored on the secondary storage devices such like magnetic disk. So pieces of program must be transferred to main memory from the secondary storage before you can execute it. Okay, since we have limited space, so large program cannot be stored in this space because multiple programs are running and they have their own process allocated to the main memory. So when a new piece of a program is to be transferred to the main memory and the main memory is full, what we will do? Then some or other piece of the main memory must be replaced. Okay, so operating system, okay, works on behalf of this requirement, and we also know that in case of cache memories, we have the similar concept. If the cache is not having the space, certainly we have to replace the block and fill with the new block. Okay, so operating system automatically transfer the data between main memory and the secondary storage. The application programmer need not to be worried, and there is no concern for the programmer, and it will be transferred by the operating system. Also, the application programmer does not need to be aware of limitation imposed by the available physical memory. So usually the programmer does not bother about the space available. Operating system will take the consideration, or basically it is bother about the space availability. So technique that automatically moves program and data, both program and data, between the memory and the secondary storage Okay, so main memory and the secondary storage, say for example SSD, we have a space. So when they are required for execution, they are called in the virtual memory by the virtual memory techniques. The program and the process reference the instruction or data independent of size of main memory. So the program will allocate the address, the processor will allocate the address. It will does not generate the address as far as the main memory address is available. Okay, so processor issues a binary address. This is very important for instruction and data. This binary address is called as virtual address. So this is independent to the available physical addresses in the main memory. So this virtual address are translated into physical address by combination of hardware and the software subsystem, and this process is basically called as virtual memory. So if virtual address refers to part of the program that is currently in the main memory, it is accessed immediately. If certain virtual address it is requested and it is available in the main memory, it can be accessed immediately. And if the address refers to part of the program that is not currently in the memory, the first it will be transferred to the main memory before it can be used, and that the operating system will take care of that. So the hardware requirement for doing this, apart from the software, is having an additional unit that is called memory management unit. So in memory management unit is used to translate the virtual address. So virtual address, or you can say logical address, comes from the processor, and the MMU will translate this virtual address into physical address. Then it will pass on to the cache and then to the physical address to fetch the data. So if desired data or instruction are in the main memory, they are fetched as described previously, and if desired data or instruction are not in the main memory, they must be transferred from the secondary storage to the main memory. So if, say for example, if the MMU says that data is not available in the main memory, so operating system will bring the process in the storage, secondary storage, and store here in the main memory. Okay, now important question that comes into mind, then certainly the process has to wait and the efficiency will come down. So at that moment, operating system takes care and stops the current executing process, suspend it, and give the another process to the CPU, which is currently in the main memory. So there will be utilization of the processor. It does not wait for the page to come into the main memory. Okay, so when the processor generates the address, the disk storage data will be transferred to main memory, and while it is being transferred, other process will be given a chance to execute the its own task. So processor will be utilized. So assume that the program and data are composed of fixed length units called pages. Okay, so what we are saying, that the logical division of a program is in form of page. Okay, so there will be another page. So page 1 and page 2. Okay, the page consists of a block of words that occupy the contiguous location in the main memory. So we very well know that the cache contains the blocks of bytes or words, that is the grouping of location in the cache. So likewise, each page is further broken into blocks, and each block is broken into the actual addressable bytes or words. So page is a basic information that is transferred between secondary storage and the main memory. So in between these, what is being transferred? In between this page is being transferred, and the hardware that is responsible for doing this is DMA transfer, that we will discuss in the when we describe in detail in unit 5, the IO mode. Okay, so basically disk storage is connected to IO interface, so the data will be transferred in form of page through IO interface to the main memory. So pages should not be too small. That is very important consideration, because the access time of secondary storage device is much larger than the main memory. So if we keep the page size small, and we know that the time between transfer of data from main memory to this storage is very high. So for a small page, why will bring data from this storage again and again? So it should not be very small. And also if it is too large, there is another problem, that is page may not be used or underutilized. It will occupy valuable space in the main memory. Basically the page space will be given to the particular program, and the portion of the page will be underutilized. So the main program will be within this, and the rest of the page will be blank. So this will be underutilized. So too big and too small is a challenge. So there should be optimal page size, and it is determined by the operating system based on the statistical analysis by various sizes of programs available and how much space it is requiring in the main memory. So concept of virtual memory are similar to the concept of cache that we have discussed earlier. So cache memory that we have introduced earlier is meant for bridging the speed gap between the processor and the main memory, and basically it is totally implemented in hardware. While in case of the virtual memory, it is used to bridge the speed gap between the main memory and the secondary storage. So we can thought of that like cache is connected to main memory to bridge the gap of speed requirement. Why should I go again and again for the main memory? It is time consuming. So I will fetch the data from the cache. Okay. Similarly, when we are having virtual memory, if there is a not availability of page, I have to go back to the secondary storage. So what we will do, we will bring a page and store in the main memory. Okay. So important thing that it is not totally a hardware concept, it is a hardware plus a software concept. So it is implemented by part software. So each virtual or logical address generated by the processor is interpreted as a virtual page number. So there are two parts, virtual page number, okay, and the second part is the offset. Okay, so this is the virtual page number plus the offset. So for virtual page number, we will use the higher order bits, so we can identify how many pages are possible. Okay, the offset will give the within the page particular address location, the specified location of particular byte within the page. So information about the main memory location of each page is kept in the page table. This is very important thing. Now, if we are keeping the page in the main memory, so we need to track which particular page is available in the main memory, or basically we can say the page table will maintain the where a particular page will go. So page table contains the index for the all the pages available in the main memory, and the main memory address where page is stored is called as page table, and it stores the current status also. So basically it is a extra data structure to store the reference to the pages that brought to the main memory, and it is stored in the main memory that holds the page called page frame. Okay, so page table contains the address of the page frame where that particular page will be stored in the main memory. So it has the starting address of page table kept, and that is called as page table base register. Now the starting address of the page table is kept in a particular register which points to a particular location where the page table will start. So we can refer again and again page table by going to the page table base register. So virtual page number generated by the processor is added to the contents of the page table base register to reach to a particular location in the page table. So this provides the address of the corresponding entry in the page table. We can see in the next diagram the content of this location in the page table gives the starting address, okay, of the page if it is available, okay, and currently available in the main memory, okay, if it is available. So you can see here there is one special register that is called as page table base register, which has the pointer to the starting of page table. Okay. So when a virtual address or logical address is generated, it has two parts, virtual page and offset. Virtual page will go to the a hardware that add a page table with the virtual page number, and it will point to a particular location in the page table. Here there are two entries. One part is control bit and another part is the page frame where the particular page will be available. So by reading this page frame number, we will add this page frame number with the offset, and this will give the physical address. So what is the purpose of this control bit? Okay, so page table entry for page table also includes some control bits which describes the status of the page while it is in the main memory. One bit indicates the validity of the page. What does validity means? Whether the page is actually loaded into the main memory. If it is available, it is as 1. If it is not available, it is 0. So it will allow operating system to invalidate page without actually removing it. Now it is time consuming to re-update update the page to the main memory. So if it is not used, we can simply convert 1 to 0. So if a page table is entry having control bit as 1 to 0, it means that the page is now invalid, it is not required. So we do not copy back it to the secondary storage. Since it is invalidated, it is not required to be updated in the secondary storage. Another bit that is used, page table has been modified during this residency in the that is having a very important use. In the first case, if it is not modified, we will simply invalidate by changing 1 to 0. But if it is modified, what we have to do? So this bit determines page should not be written back to the disk when it is removed from the memory. So this is a caution. So if it is modified, bit is set to 1, operating system cannot update it or remove it until unless it is updated back to the disk. So similar to dirty bit we are using in the cache memory. So we can say that this invalidate bit that indicates the modified status is similar to the dirty bit concept in the cache memory. Okay. Other control bits of various types of restrictions may be imposed, like when multi-programming is there, we do not give permission to other processes to modify. So there might be some control bits so that they can restrict other process that is not a main process. They can only read, they cannot write. Okay. So where should the page table be located? Now page table is used by MMU for every read and write access to the memory. This is a very important thing. So the MMU will always refer this page table. So if we keep the page table in the MMU, so MMU is a hardware and the page table is quite large because for every page there will be a index available. So MU implemented as a part of processor chip. So it is impossible to include complete page table on the chip. So page table is kept in the main memory. So where is page table kept? Page table is kept in the main memory. Why? Because there is a limitation of MMU and it cannot increase a very large page table entries. Okay, so hardware space has a limitation. So what it do? It copy a small portion of the page table and accommodate within the AMU. The portion consists of page table entries that correspond to most recently accessed page. Okay. So it is good choice that we will keep all the page entries that is most recently accessed in the AMMU. So most likely that date will be accessed again. So it is having a high chances that we will refer the data from the page table kept in the MMU in a small portion of the page table. So a small cache is used here, and that cache is called as translation look aside buffer, and it is a part of MMU. So you can say that MMU has having a certain memory space. So this TLB holds the page table entries that is most recently accessed. So we can easily recall that we have been doing in the cache memory also. Though recall that the cache memory holds the most recently accessed blocks. So here instead of we keep the block, we are keeping the most recently accessed pages. So operation of TLB and page table in the main memory is similar operation as cache memory and the main memory. So we can have an analogy here. Page table entry for page include address of the page frame where the page is residing in the main memory and some control bits. So as we have seen in the page table, so the page table that is a part of the TLB will also have the page frame entry and some control bit. In addition to above each page, TLB must hold the virtual page number of each page. Now this is a very important thing. You can see in this diagram, apart from control bit and the page frame, it also have a virtual page number. Why? Because we do not go to the page table to read the virtual page number. Why? Because then it will create extra word. And beautiful thing is there that the virtual page number is compared with the generated virtual page using associative comparison. So in one go, it will easily find whether the virtual page is available in the TLB's cache. Okay, so this is very important thing. The virtual page number available in this TLB will be checked together with the virtual page number requested. Okay, so in one go it will say hit. If it is hit, it will go and add with the offset and it will generate the virtual physical page number. So it should be noted that the TLB memory is basically a memory which is associative mapped, and because of associative map, this comparison is not a time consuming process. An additional column of virtual page is available in the TLB. Okay. So how to keep the entries of TLB coherent with the contents of page table in the memory? Since there are two copies, one copy is in the TLB, another is in the page table. The whole copy is in the page table and the part of that is kept in the TLB. So it should not be a coherent? Yes, it should be a coherent with the contents of the page table in the memory. So operating system may change the content of the page table in the main memory. Yeah, it can update. So it should be simultaneously must be invalidate the corresponding entries in TLB. If there is a change in the page table, it should be reflected back into the TLB. Otherwise, there will be mismatch. So that is called as coherency. So a control bit is provided in the TLB to invalidate an entry. Okay. If entry is invalidated, then the TLB gets the information for entry from the page table. Okay. So it follows that the same process that it would follow the entry not found, and there will be miss occur. Okay, here you can see if it is entry is not available, it will generate the miss. Okay, now what happens if program generates an SS2 page that is not in the main memory? In that case, page fault occur. Okay, you will be doing the problem of page fault. So whole page must be brought into the main memory from the disk before the execution can proceed. So I have earlier discussed also, I have to bring, then CPU has to wait. So upon detecting the page fault by the MMU, following action may occur. The MMU asks operating system to intervene by raising the exception. Processing of active tasks which cause the page fault is interrupted. It is stopped. It won't be working. And the control is transferred to the operating system. And operating system copies the requested page from the secondary storage to the main memory. And when page is copied, control is returned back to the interrupted task. And during that period, what will happen? Should processor be waiting? No. The CPU processor will be given another task. Okay. So servicing of page fault requires that transferring of requested page from the secondary storage to the main memory. This transfer incur a long delay. Okay. So while page is being transferred to the operating system, so after suspension, what will happen? We can execute another task whose page are in the main memory. That enables efficient use of the processor. That is very important requirement. Processor, if it is ideal, it is wasting the valuable resource. How to ensure that the interrupted task can continue correctly when it resumes execution? Yes, there are two possibilities. One is the execution of interrupted task must continue from the same point where it has been interrupted. The instruction must be restarted. Which specific option is followed depends upon the design of the process. Okay, it will depend upon the processor. We should restart or you will become. So if you have to restart, certainly there will be some stack or there will be some mechanism by which you can bring back the starting point. So when new page is to be brought in the main memory from the storage, the main memory will be full. Some pages of the main memory must be replaced by new page that we are doing in the cache. So how to choose which page to be replaced? So we can use the similar strategy we use in the cache. The principle of locality reference can be used to applied here, and replacement strategy similar to LRU can be applied. Since the size of the main memory is relatively larger compared to the cache, a relative large amount of programs and data can be held in the main memory. So minimize the frequency of transfer between secondary storage and the main memory. Page may be modified during the residency in the main memory. When should the page return back to the secondary storage? Recall that we encountered similar problem in context of cache. So write through and write back protocol is required. Write through means immediate, write back means it will wait till the next cycle. So write through protocol cannot be used since it will incur a long delay. Time, small amount of data is written to the disk. So this is very important consideration. If we do immediate update and there is a high time, access time between memory and the hard disk, so why should we do each and every time update? So write through is not good for the virtual memory. We will go for the write back protocol whenever the next cycle comes. So operating system is concerned with transferring program from data between memory and the storage. The operating system needs memory routines. Separate program is written addition to other routines. Operating system routines are assembled in the virtual address space called system space, and system space is a separate form of space which uses application program beside, and this is the user space. The virtual address space is divided into one system space plus several user address space. So recall that the memory management unit translates logical address to virtual address. The MMU uses contents of page table base register to determine the address of the page table to be used for translation. So changing the content of page table base register can enable us to use different page table and switch from one space to another. That is a very interesting thing, that if we change the page table base register address, we can keep on changing the page table data. So at a given time, page table base register can be pointed to one page table. Thus only one page table can be used for a translation process of given time, and pages belonging to only one space are accessible at any given time. Thank you and Jai Hind everyone for this lecture. I hope you understood the concept. So we will be starting the some problems based on the replacement algorithm in case the page is not available in the main memory and the stretching. Thank you.